The JS ecosystem makes developing JS apps fast, but installing libraries hurt the bundle size. It is normal for a JS app to be 1 to 5 megabytes before gzipped. This means that the client has to parse at least 1 MB of JS code to make any sense. This might not be a problem for shiny MacBooks, but is definitely a concern for low-end mobile hardware. Shadow provides us an efficient API to analyze and split our code into smaller chunks. Before we get into the details of code splitting, we need a way to measure where we stand. Shadow comes with a built-in reporting tool that lists the size and ingredients of bundled modules. We can generate a report using yarn report command. This report command was set up by Create Shadow CLJS app. After running this command, the output will be printed to your terminal and also in a file called report.html. Our app is currently 625 kilobyte gzipped without any code splitting. The report also tells us about the elephants in the room. The 4 most heavy modules consist of 50% of the code. Our project files, i.e. the code we wrote, are only 1.3% of the compiled code. We will try and optimize this and regenerate reports to check our progress. The process of code splitting includes 2 steps: configuring the compiler and modifying the app to load split code. With just one large bundle, we don't need to worry if our code is loaded yet. But with multiple smaller bundles, we need to ensure that all required code is available. One way to split code is to bundle code by routes, i.e. have one module per route. We have 3 main routes that we can split for: login, register, and graphics. In the real world, you might also want to split out heavy components. For example, in our case, we can't really do anything about Blueprint because that's a UI layer. But Firebase and Fabric are not needed to render the index route. Shadow splits code by clubbing entry points into modules. Modules is a generic term, but you can think of splitting out modules as files. Currently, our Shadow configuration only generates one module main, i.e. only one file main.js that we load in index.html. Let's update our configuration to generate one module per route. Module loader true injects additional code that enables fetching of modules at runtime. We added 3 additional modules: login, register, and graphics. This will lead to the creation of login.js, register.js, and graphics.js along with main.js in the configured output directory. Only one module needs to be dependency-free, i.e. the root module that's absolutely needed for app to work. Other modules can mark dependencies using the depends on configuration, which accepts a set. It is possible to depend on more than one module. All modules need to depend on the root module. The entries key accepts a vector of namespaces that needs to be clubbed inside that module. Shadow computes the dependency graph and tries its best to put most code outside the root module. Think of it trying to generate a small main file and pushing heavy components to other modules. However, this is not always accurate and requires tuning. We have the modules now, but if you run the app as it is, Shadow will complain about not being able to split. This is because the modules we split out are not being loaded dynamically. Since we split out modules by routes, and our routes are reagent components, we need to create a component capable of lazy loading modules. For other code which is not in React lifecycle, shadow.loader/load function can be used to load modules as needed. Load returns a goop.async non-deferred and can be used like a promise. The string extra is the name of the module that we defined and could be main or login in our example. We need to create a lazy component because there is no easy way to use a promise with React Router. Let's create a lazy component to load our React components dynamically. We use the Shadow lazy namespace and call load method on the loadable argument in component didMount. Loadable is the component we want to load. The load function accepts a loadable and a callback. Our callback updates the loaded state to true. Then, in the render method, we check if the loaded state is true and render accordingly. Loadable is an atom-like object that can be dereferenced to get the dynamically loaded module. The dynamically loaded module in our case will be a reagent component, so we can render it as vector loadable. This will make sense just in a moment. Shadow is not able to split modules because app.code requires all pages, essentially leading to a graph that cannot be split. We can safely remove the vectors that require login, register, and graphics page. Now, we need to load these modules using the lazy component. For this, we need to require the lazy component and the shadow lazy package. Finally, we can update the root router to render components lazily. We replace the actual components with lazy comp and pass the additional component to SL loadable. Shadow lazy loadable is a macro that takes a namespace qualified definition, figures out the module it is present in, and provides an API to load this module. SL loadable is a macro and not a function, hence cannot be moved inside the lazy comp definition. This is passed as the loadable argument to lazy comp, which when dereferenced using @ returns the component. Now if we load the app in logged in state and navigate from index to login page, you will see a network call to load login.js and probably a message that says lazy loading. Using lazy comp directly didn't work for graphics route, as React router's redirect has some issues with switch and it prevents component from re-rendering. You can check the link to Stack Overflow and GitHub issues in the chapter notes. By adding an extra wrapper graphics container, the component loads fine. If we check the report again, you will notice that we have reduced the bundle size to 1.83 MB, which was more than 2 MB earlier. This was mainly because Fabric was split out and moved to graphics module. Depending on your app, you might be able to create more modules and save more bytes initially, leading to a snappy UX. In this chapter, we understood Shadow's lazy loading mechanism. We then configured Shadow to split the app into smaller modules and updated the code with the ability to load modules at runtime.